Jai Hind, welcome to the course Network Analysis and Synthesis, and today I am going to discuss about the maximum power theorem applied to the AC circuits. So, the learning objectives of today's lecture are: first we will go for the state and prove maximum power transfer theorem applied to AC circuits. First we will discuss the theoretical part of this theorem. Then we do some problems related to maximum power transfer theorem. So, to carry out the problems related to maximum power transfer theorem, there are certain steps. So, what are those steps? First, we find the equivalent impedance of the network across load terminals. So, first and foremost, if you were required to find the maximum power transfer to the load, first remove the load from the network and find the equivalent impedance across the load. Okay, that is the Thevenin equivalent. So, what we did in Thevenin's theorem, Thevenin equivalent we have to find out here. So, we can say the application of Thevenin's theorem in maximum power transfer theorem. The second step is find the voltage across load terminals. So, just remove the load from the network, the circuit becomes open circuit. So, find the voltage across the load terminal, so that is the open circuit voltage, or we can say that is the Thevenin voltage, VTH, what we did in the Thevenin's theorem. Then third is the find the maximum power. So, maximum power is P max is VTH square upon 4 RL. So, these are the three steps you have to follow while solving the problems related to maximum power transfer theorem. So, first we go for the first part, that is the state and prove maximum power transfer theorem applied to AC circuits. So, what is the statement? A statement of the maximum power theorem is the maximum power will be transferred by a network to the load impedance, say it is ZL, if the load impedance is complex conjugate of the source impedance of the network, or you can say the impedance of the network as seen from the load terminals. So, that is if ZL is the load impedance. So, to have the maximum power, this ZL should be complex conjugate of this Z. So, this Z is this Z is the impedance of the network. So, if the source impedance say it is coming RS plus JSS. So, to have maximum power transfer, the load impedance must be RS minus plus JXS, complex conjugate of the this. Okay. So, this is the statement of the maximum power transfer theorem, just then we will prove it. So, for the proof, take the simple circuit having the one voltage source, this V, and this is the load impedance, this is the source impedance, I say, and this the current is flowing through this load is say I. And we are considering the case 1 where the load impedance is complex in nature. So, load may be complex in nature, load may be the purely resistive. So, we will take these two cases independently. First we go for the load when it is complex in nature. So let V be the voltage source. So, this is the supply voltage of the network. RS and JXS is the source impedance, and the internal impedance and this is the RL plus JXL is the load impedance. So, the current I will be simple Ohm's law, I is equal to V upon Z. So, total impedance of the network is this impedance plus this one. So, I is equal to V upon ZS plus ZL. Say ZS is equal to, this is nothing but this is ZS and this is nothing but this is your ZL. So, we can put here. So, this is the expression for I. Now, the average power delivered to the load will be I square RL. The average power delivered to the load will be I square RL. So, put this expression in the this equation. So, this is the average power delivered to the load, P is equal to I square RL. So, this expression we are getting. Simply, just from here we can get this one. Vs square, okay, then this is this RL, this one, and then Rs plus R x square, okay. So we can find the average power delivered to load. Now we have to find the maximum power transfer to the load. So we know that for maxima minima, what we have to do, we have to differentiate this power with respect to these two variables, with respect to RL and XL. So say first consider RL to be constant and find the maximum power equating dP upon dXL equal to 0. So just differentiate this equation with respect to XL and we get this expression, okay. So differentiating the previous one, we are getting this and this, and it should be equal to 0 for maximum power. So we can see that this can only be 0 if minus 2 V square RL XL plus XS is equal to 0. So this can only be 0 if the numerator is 0. Clear? So this can be 0, so we can write this expression. At the same time, we can see that this can only be 0 if this is equal to 0, either this 0 or this 0 or this 0. If any of these three terms V, RL and summation of XL plus XS, if any of these two terms are equal to 0, the expression in the numerator becomes the 0. Now the question is V with the 0 or RL with the 0? The answer is not. Why? Because V is the supply voltage. It has to supply the power to the load, so it cannot be 0. So V cannot be 0. V cannot be 0 because it has to supply the power. It has to supply the power. And RL can also not be equal to, cannot be 0 because it have to absorb the power. So this V cannot be 0 and this RL cannot be 0. So only expression is XL plus XS is equal to 0. So we can get this expression. So XL plus XS is equal to 0. Clear? So there are three terms, this and this. Only this can be equal to 0 to have numerator terms into 0. V and RL cannot be 0 because one is the supplying power to the load and the other one is absorbing power from the source. So XL is equal to minus XS. Now put here. So this is the expression for power V square RL plus RS square. Now differentiate this expression with respect to RL. We get this expression we are getting. Okay. So this can only be equal to 0 if the numerator part is 0. So this numerator is 0. So just, and similarly we can see that this cannot be, a square cannot be 0. So on simplification we get RL is equal to RS. So this cannot be 0, this cannot be 0, okay. So RL is equal to RS. So to have the maximum power transfer, what we have obtained? ZL is equal to, this is the expression for the load impedance RL plus XL, and RL is equal to RS from here, this one, and this XL is equal to minus XS here. So we put this one, so we get this. So ZL is the complex conjugate. So this is basically Z. This is Z. R minus J XS, which is equal to ZL. Complex conjugate. Okay. So to have the maximum power transfer theorem, according to maximum power transfer theorem, to have the maximum power, the load impedance must be complex conjugate of the source impedance. Now come to the case 2, when the load is purely resistive. So similar expression, this is the supply. This is the supply I. Okay. So I say this is IL. Okay. So current through the load impedance is V upon simple Ohm's law. Then average power delivered to the load I square RL. So I square, this one is I square and this is RL. Now differentiate this expression with respect to RL. So we are getting this. So dP RL upon RL equal to 0 to have the maximum power. So differentiating, we get this expression. Okay. So this can only be 0 if the numerator is 0. So take the numerator, and we also can see that this term cannot be 0, supply cannot be 0. So this is equal to 0. So this is. So basically RL is mod ZS, mod ZS. So when the load is purely resistive, to have the maximum power transfer theorem, RL must be RS square plus XS square, which is nothing but ZS, magnitude of the ZS. So here a student commits mistake. In place of taking magnitude, this RS square plus XS square, they just consider RS is equal to RL and solve. So that is the mistakes students generally commit in this case when the load is purely resistive. So be careful. So what should be the efficiency of the maximum power? So efficiency of the maximum power, this is the power absorbed by the maximum power absorbed by the load, and when RS is equal to RL, so this is the power absorbed by the load, and we can see here that RL is equal to RS. So power absorbed by the source impedance is also equal to V square upon 4 RS. If we combine these two, V square plus V square upon 4 RL, so here we can write PS max is equal to V square upon 4 RS. So P max is equal to PL max plus PS max. So it is V square upon 2 RL. So efficiency is 50%. So in case of the maximum power transfer theorem, the efficiency is 50%. So this is the all theory about this theorem. So when the what we conclude here, case 1, when load is complex in nature, ZL is equal to complex conjugate of the source impedance ZS, and case 2, when load is purely resistive, in this case RS is equal to RL is equal to RS square plus XS square, which is nothing but ZS magnitude. So be careful in this case. When the load is purely resistive, to have the maximum power, we have to use this expression. When the load is complex in nature, we have to this one. So RS minus plus XL. Okay, and we can see that ZS is equal to RS plus minus JXS. Okay, if this is the load, this is the source impedance. So to have the maximum power, it will be RS minus plus XS. Suppose here it is RS minus plus, so here it will be RS plus minus, complex conjugate. Now do some problems. So first problem is for the network shown below. Determine the impedance ZL such that maximum power is transferred from the source to load impedance ZL, and also find the maximum power. So here in this case there are two parts of this problem. One, we have to find this ZL, okay, and second part is maximum power, which is VTH square upon 4RL. So how we'll do it? What are the steps? First step is just remove this ZL from the circuit and find the equivalent impedance of this network and replace this independent sources by their internal impedance, and find the equivalent impedance as seen from the load terminals. So what are the steps? Steps is determine the equivalent impedance across the load terminals, that is ZTH. Find the open circuit voltage across the load terminals. So you have to find the voltage here. Say this terminal is VAB. So this voltage is different here. So you have to find the voltage across VAB. Be careful. In derivations, I have used this supply voltage because there is no impedance. So if you open the circuit, this voltage is appearing here. Okay. So here you have to be careful. You have to find this open circuit voltage, means across the AB terminals, which is nothing but VTH, and then find the maximum power transfer, which is P max is equal to VTH square upon 4R. So these steps you have to follow while solving the problem related to the maximum power transfer theorem. So first step is find this ZTH. So remove this ZL from the load. So just removed, and see, just you have to see from here. Okay. So when we see from the load terminals, so we can see that if we put here some supply, the current will flow like this. So this current and this current. So we can see that this and this impedance, they are there. They are in parallel, and they are parallel in series with this. We have to see from load terminals. So ZTH will be minus J2 this, and the parallel of this. So minus 1. So ZTH is minus J2 plus parallel combination of 1 and J1. So this you have to obtain. So we can get this. So minus 2, 1 J1, 1 plus J1. So look at here. Then you have to convert this. How will we add it? So this is in the rectangular form. Now this first we convert it, this in the polar form because magnitude and phase angle. So convert into the rectangular and we get this. So finally we are getting this for this one and this. So how can I add it? You have to convert into, this is polar to rectangular, polar to rectangular. Okay, then we can add. Okay. So this is your ZTH. So this ZTH is minus 5 J 1.5. So this is the equivalent impedance of the network as seen from the load terminals. Okay. Now what should be the ZTH? ZTH should be the complex conjugate. This is the Z, not this is ZL. So it should be the complex conjugate. So it should be ZL should be this one, complex conjugate of ZTH. Okay. So ZL is complex conjugate of the ZTH. The first step is you have to find the equivalent impedance of the network as seen from the load terminal, that is the ZTH. Once you find ZTH, take the complex conjugate. So this is the ZL. Now come to the determination of VAB. VAB is the load terminals. So you have to find the voltage across the load terminals. That is the VTH. So we can see here, I can redraw this network here. We can see what is this one. This. So simply, this is open. So I am taking this. So this is open. Okay. So here I can write draw the expression. This is your 5 angle 0 degree volt. Okay, and this is 1 ohm, this is J1 minus J2, and this is the AB. So you have to find VAB, which is nothing but open circuit voltage. So look at here, what is the voltage across this? This terminal is open, so no current will flow through the minus J. इसको हटा दीजिएगा लेकिन से कल भी गिर गया था, पता नहीं गिर जाता है. So this terminal is opened, AB terminal is opened. So this 5 volt voltage source is supplying power. This current will flow like this. Here will be no current. Okay, current I is equal to 0. Here 0. So current is flowing in this loop. So what will the VAB? VAB the voltage across this J ohm. So VAB is nothing but I into J1. I into J1. So what is I? I is nothing but 5 angle 0 degree and total impedance 1 plus J1 into J1. Clear? So VAB is the voltage across this, because there is no drop across this one. Because why? Because of this terminal, this path is opened. So current must have a return path. So current will flow, no current will flow through the AB terminals in this case. So drop across minus J2 ohm will be 0. So whatever the voltage is developing across J1, that will be the VAB. So VAB, this is the current and this is the impedance. So you can look here. So this is the voltage across, voltage drop across the, this is the current through the J1, and we multiplied with this is then the voltage across the J1, and that voltage will develop across the AB terminals. So this is this, and we are getting this. So this is different from, this is the VAB. Be careful. So now Pmax. So Pmax is VAB square upon 4RL. So this is, and RL we can obtain, this is RL. So this is RL plus JXL. Okay. So this RL we can get. So this is the way we can. So this is the maximum power, 6.3 watt. So these are the steps you have to follow while finding the maximum power using the maximum power transfer theorem. Now come another problem. So for the network shown below, the load consists of a capacitive reactance of this 15 ohm and variable resistance RL. This is load resistance. determining the value of RL for which the power transferred is maximum and value of maximum power. So what you have to find? We have to find value of RL. What it should be? It should be RL is equal to RS square plus XS square, which is nothing but mod ZS, okay, and maximum power P max. So P max is equal to VTH square upon 4 RL, okay. So ZS is this is the source impedance, and then the I is equal to simple Ohm's law, V upon total impedance of the network. Then we got the expression for power, okay. Now to have the maximum power transfer, what you have to do? We have to differentiate dP L upon DRL. So we get this, So simple. So this can only be 0 if this one is 0. So 100. So 100 square 10 plus RL square plus 25 minus 2 RL 10 plus RL is equal to 0, okay. So this cannot be 0, this cannot be 0 because it has to supply the power. So this, so we can RL is equal to 100 plus 25, so it is so RL is equal to root over 125, so it is 11.118. PL max is VAB square upon 4 RL, okay. So why it is 100? Because look at the network is like this. So once we open this, when you remove this terminal, so it becomes open, so no current will flow. No current will flow through this. When the circuit is opened, no current will flow through the 10 plus J10 ohm. Okay. So voltage across this will be 0. So whatever is supplying voltage, that will appear across the AB. So that's why we, in this case, VAB is equal to source voltage. So don't confuse. Okay. So this is, and this is your RL, and this is the wattage. So this way we can solve maximum power transfer theorem. The steps are very simple. Find the ZTH, find ZTH steps, find ZTH, find the equivalent impedance of the network, okay, that is ZTH. So ZL is ZTH complex conjugate of the ZTH, okay. When the load is complex in nature, when the load is complex in nature. Okay. ZL is equal to mod ZS, or you can say RS square plus XS square. when the load is purely resistive, and maximum students commit mistake here. Load is purely resistive. Be careful in this case when the load is purely resistive here. And third is P max is, I am again writing here VTH square upon 4 RL. Sometimes VTH is coming the supply voltage, okay, in some cases, but you have to obtain the VTH square upon 4 RL. Okay, this is not the supply voltage, this is the voltage AP, that is the open circuit voltage across the load terminals. So this these are the steps you have to follow while solving the problems related to the maximum power transfer theorem. So this is all about your maximum power transfer theorem. The questions may be either, if you theoretical as far as theoretical part is concerned, they may ask state and prove maximum power transfer theorem applied to AC circuit. So what you have to do, you have to write the statement and then you have to prove the theorem. The second way of asking the question related to the maximum power transfer theorem is they may ask this type of two numericals. Okay, the circuit may be different but approach is same. There are 3 steps. First, find the equivalent impedance of the network. Take the complex conjugate if the load is complex in nature. If the load is purely resistive, then take the magnitude of the source impedance or equivalent impedance of the network. That we did in this case. And then find the maximum power, which is VTH square upon 4 RL. So this is all about maximum power transfer theorem. So I am stopping here. Thank you very much. In the next lecture, we can have some other topics of this course. Jai Hind.